paper for the conference. We had some ideas, and what's happened in the meantime, these ideas have changed quite a bit. So, in a way, this presentation might be a little bit confusing because in our own minds, our investigations around this topic are really quite fluid. So what I'll do is try to be as systematic and as organised as I can in order to convey, I think, what we think are the important essential elements. The title of the talk mentions contextuality, and this is one of the things that we've been very, very interested in investigating. And in particular, the question is there contextuality in human information processing? And in our talk yesterday with Lauren, I mentioned that so far the experiments that have been produced in the quantum cognition community have been largely negative in that respect, except for one that Zafarov did recently at the end of 2017. So the first part of the talk will be essentially conceptual, trying to set the scene around this issue of contextuality. And the first thing I wanted to bring up is this notion of probabilistic reductionism. So this is a term I discovered from a researcher in economics, where they also developed probabilistic models. And I think I think the basic tenets of probabilistic reductionism are also relevant to the way we develop probabilistic models of cognitive phenomena. Right, so how do we go about developing these models? Right, so the probabilistic reductionism says, well, what we do is we reduce some aspect of the phenomena of interest to one or more random variables. Okay, and then the second tenet is that once we've got this random variables, that the model that we're dealing with is a joint probability distribution of those random variables. So here we can see an example from a paper they took out of a cognitive science journal, and then they're trying to understand the human perceptual mechanism. And here you can see those rectangles represent the random variables. So one of them might be a reduction of a group of neurons in the left eye, another one might be a reduction of a group of neurons in the right eye. And there we can see 5 rectangles, so we're dealing with the joint probability distribution over 5 random variables. So this I think is a very, very unstated, it's an unstated approach that we take in order to develop these probabilistic models of cognitive phenomena. Now, so how does contextuality enter into the picture? For those who don't know what contextuality is, even in physics, this is really quite a subtle issue. And in my own investigations in this years, it's taken me, in fact, years in order to try and understand what contextuality is from an intuitive point of view. Because the mathematical descriptions are very, very clear and precise. And as a community, if we're going to talk about contextuality, we need to talk about it in a way that's relevant to us. And so one of the best definitions for this is one that Acacia Barras and OAS came up with in 2015. And they said this: contextuality is the impossibility of assigning a single random variable to represent the outcomes of the same measurement procedure under different experimental conditions. Now you can see already the danger to probabilistic reductionism, because when we design our models, we come up with these random variables initially. We've reduced some element of the cognitive phenomena to the random variables, and we do this usually prior to thinking about the experimental context or the conditions in which we investigate them. Now, there's an intuition that I'm going to run with in this talk, and that contextuality, as defined by that, and how we develop our probabilistic models, is similar to a problem that occurred in programming languages in the 60s and 70s. So where, I'm going to demonstrate this in a moment, where a random variable it is essentially behaving like a local variable, right? But the point is that the way that we're developing our probabilistic models, we're assuming that all the variables are global. So it's distinction between local versus global random variables. And so, as I said this before, contextuality undermines probabilistic reductionism because random variables do not have, when the system is contextual, don't have this unique global functional identity which we assume according to principles of probabilistic reductionism. So this is an example of a program. So some of us here are probably old enough to remember programming languages in the early days when we were looking at the 60s and 70s. And in those days there was a language called Fortran where you could develop a program and all of the variables are global. So in this program here we have a variable x at the top which is given some initial value. And then in those days the programs could become very, very long, and halfway down the program suddenly you might overwrite the variable x with something else. And the reason why you've done that is because when you're developing the program you have a particular purpose for that variable, you have a particular functional identity in mind for that variable, and as you're developing the program you forget that and you start using it for something else. And then, as a consequence, the program has an error. It's above is introduced. Now, at the time when programming languages were being developed, this was a recognised problem. And then there was a paper that came out, I think, in the 70s, which was titled "Global Variables Considered Harmful." And one of the reasons why they were considered harmful was exactly this problem where because in the act of programming, you forget the functional identities of the variables that you're dealing with, and as a consequence you introduce errors. So the intuition that I've been sort of harbouring for quite some time is that the way we develop probabilistic models at the moment is very, very similar to the status of programming languages at that time, like Fortran, where we're assuming that our variables are all global, right? Whereas in fact, the contextuality is suggesting, in a programming language sense, that our variables aren't always global, or don't assume this unique functional identity that is accorded to them prior to when you use them in various measurement contexts and measure them. So that's I'm going to continue that intuition as we go along. You probably can't see that program up there, but the idea that we've been trying to run with is the following. So we would like to develop probabilistic models where not all the variables are global, that you can actually have variables local to the measurement context, but still you can overload the label of the variable. So here up the top we've got two measurement contexts. So we're attempting to define special program syntax to define the measurement context, and you define the variables as being local to a particular measurement context. So at the top you've got a variable A1, and down the below you've got another measurement context A1. So we're using the same variable named A1, but just like in programming languages or modern programming languages, this variable A1 might have a different functional identity local to the context in which it is being used. So we're trying to come up with special syntactic constructs to express these probabilistic models, and in particular the measurement concepts we use. We can declare random variables local to that context, and we want to be able to use these programs as a way to simulate experiments in order to determine whether something's contextual. So maybe what I can summarise the proceeding in the following. We're looking to use these probabilistic programming languages to come up with more sensitive probabilistic models. And these more sensitive probabilistic models will allow us then to be able to investigate contextuality. So that sensitivity, as we see as I go along, will not only be expressed in terms of the syntax which we use to define the programming language, but also, more importantly today, is the how we're going to deal with the underlying semantics of the programming language. But so that's the aims, and that was originally what we had in was we put down in this paper. But one of the things that we came across is the following problem, because probabilistic programming languages have been developed essentially to manipulate probabilistic models, right? So, and these probabilistic models adhere to classical notions of probability theory. Now, if you want to simulate a quantum experiment, like an EPR experiment, the correlations in those experiments can go beyond what is classically possible. So the problem that you have is, how do you take a probabilistic programming framework, which is using classical probability theory, and try to do something quantum? And by that I mean specifically, how do you get it to produce quantum correlations? Because the underlying framework is all classical. So this is the problem we ran into, and then for the rest of the talk I'm going to try and show you a particular theoretical framework that's come out of quantum information science that we found very, very helpful in order to embed in the programming language framework in order to be able to do this. So I'll show you, and this is where the talk becomes more technical, but I hope that I'm able to convey some of the basic ideas behind this, and towards the end I'll be showing some simulations that we did. Yeah, Bart, you got a question?
Yeah, clarification what you're trying to do. So you're trying to achieve quantum correlations somehow by reconstructing the language.
Yeah.
The standard way, one standard way of doing this classically is you have two states. Yeah, you in the language that you used before, you update with the predicate on both variables involved. That creates dependence. That could be done in principle in quantum setting as well.
Yeah. So that's right. But what we want to be able to have is that the underlying framework can serve more purposes than just that. And it's not only quantum correlations that we eventually want to be able to simulate. So it's coming out with an expressive enough underlying theoretical framework to cater for all those sorts of things. Yeah.
But anyway, my point is updating creates correlation.
Yeah. So this is the EPR experiment. So the left-hand side shows a Bayesian model in order to understand it. And the 2 points, the important points to note about that left-hand diagram, we have system A and system B. And each of them are conditioned by a variable X and a variable Y. And in the middle, there was this assumed hidden variable that would, which a lot of this work in EPR experiments was an attempt to rule out.
It's a number from here. It looks like
it's a lambda. Yeah. And so that's the underlying probabilistic model. On the right hand side, you have these 4 distributions. So you might condition variable A with x equals 0 and condition variable B with y equals 0, and then you run an experiment and you collect data across the outcomes of A and B. And essentially, as we saw yesterday in our presentation, you come up with 4 pairwise distributions, which are the basis of the empirical basis of the EPR experiment. And the bottom is just a grid of 16 probabilities, and these correspond to the 16. This corresponds to the 16 probabilities that have come out of those 4 pairwise distributions. So that's the typical underlying framework of an EPR experiment. Now, this diagram is meant. Maybe I'll use this. I find it.
Perhaps.
Is this better?
Perhaps you should switch it on.
Yeah.
Mm-hmm. Try.
So
Yeah, it's good.
yeah. So Yeah.
Yeah.
So what we see here is that what we want to be able to do is we want to be able to define some probabilistic programs that have a syntactic framework for expressing different experiments. So not only the EPR experiments, but any flexible framework, all sorts of experiments where we can investigate contextuality. So, and so this syntax provides a means for expressing these different measurement contexts. And so the EPR experiment has those four that are shown on the top. And at the bottom, we have these, the programming and semantics are in terms of these things called contextuality scenarios. So these have come out of quantum information science, and they've been used to investigate contextuality in quantum physics. So what we're attempting to do is to underpin these probabilistic programs with this sort of theoretical framework. And so quite a lot of the rest of what I'll be doing is trying to explain to you the salient elements of these contextuality scenarios, and they're all just based on hypergraphs. So if you look at the literature that it's been written in terms of investigating contextuality, it's really sort of broken up into three areas. We have the generalized probability theory, so that's a particular approach that's been taken. And Zafarov in this community is an example of a researcher in that, but there are others that are quantum physicists that have looked at generalized probability theories. Another approach is to use sheaf theory. This is Bramsky from Oxford and his colleagues, and this is related to category theory. And a third approach that's sort of, I think, is quite new is hypergraph-based approaches, and these have come out of quantum physics. So there are a number of researchers that have been looking at these hypergraphs as a flexible way of investigating contextuality in quantum physics. One of the reasons why we thought that the hypergraphs are particularly relevant to this programming language framework is that they're very, very modular. So the modularity provides at least the potential for providing a flexible underlying semantics that can express a wide variety of possible experimental designs, the ones that we haven't even conceived of yet that might be relevant to this community. So here we go into it. So I'll try to explain some of just the basic elements. So when we have the system A, it's conceived of as two edges. So one edge corresponds to the outcomes that are possible when system A is conditioned when x equals 0, and the other edge has a similar outcomes over A 0, 1 when it's conditioned x equals 1. So these two together form the hypergraph semantics for system A. And similarly for B, you have a similar sort of situation. So you're starting to look at the problem. We're saying, well, I can measure system A in two ways and we get certain outcomes, and I can measure system B in two ways and I can get two different outcomes. So these map directly down into these hypergraphs as we see here. Now, I think the most interesting aspect of these sort of semantics is the composition. Right, so once we've got these basic elements, these can be composed. So this goes to this modularity. So if we have a program that's defining an experiment with different conditions, so what we can do is we can map down those different experimental conditions into modules in the semantics, and then via a composition operator, appropriate composition operator, we can express experimental constraints and other relevant details to the experiment, and these are embedded into the hypergraph semantics. So the first thing you can do is that you can form the direct product of these two hypergraphs, and then what you get then is these, it's just like a cross product or a Cartesian product, and we get these four hyperedges here by direct product. And here we can already see this is the basic structure of our experimental design. We have the four experimental conditions. In each condition, we've got A equals 0 and B equals 0. These are the outcomes. So this is the composition operator is what is expressing the joint measurement between the two systems. Right, so this is really neatly taken care of in these sort of hypergraph semantics. But the problem you have is that even though this gives you the basic structure of the experiment in terms of these 4 pairwise distributions, but it doesn't yet express the no signaling condition, which is of course intrinsic to the EPR experiment. So how is it that we're going to bring in the no signaling condition, and how is it going to be expressed in terms of the underlying hypergraph? So I'll talk about that next. So this is just some technical detail, but the thing about once we've got the underlying hypergraph, you've got to think about there is each of these hyperedges, they have a probability distribution over the outcomes. And these probabilities might come from the experiments that you've conducted, so, in a laboratory, for example. And the thing is that we have to impose certain constraints. So you can see that the no signaling condition is expressed in terms of particular constraints on outcomes and hyperedges. So that's the technical detail. But I'll give you an example or the intuition of what's happening is these sorts of constraints, and there's there's 2 of them. This particular one expresses that the sum of these probabilities of this hyperedge must be the same as these probabilities of this hyperedge. And this ensures that when you make a measurement on system A, that its marginal probability is not affected by what you're doing over at system B. So this is how this is expressed in the hypergraphs. So you have 4 of those probabilistic conditions over the hyperedges, and you have another 4 that go across this way, and this way you can express what no signaling looks like in this hypergraph framework. Now, how do you actually make sure that the probabilities adhere to this condition? Because we're using a composition operator to compose system A with system B. So when we're composing the 2 systems, we have to make sure that the no signaling constraint is expressed in the underlying hypergraph structure. And there is this product known as the fullest Randall product, which does this. But the point here is that you wouldn't always use the fullest Randall product. The fullest Randall product is chosen because it has its mathematical consequence is it provides an underlying hypergraph structure that adheres to the no signaling condition. If you have experiments where signaling is permitted, then you would develop other composition operators in order to express that. So that means that if we have a variety of different experimental designs, what we need to be able to do is come up with the composition operators that appropriately express the constraints that are inherent to the design that you're interested in. So here's a lot of technical detail, but so essentially you can see here that what it's doing is that the fullest random product is taking sort of an element of an outcome from system A, say, and mapping it to an edge in system B. So for example, we've got an outcome here from system A, and what we do is that's mapped to a particular hyperedge here, this red one here, and then this other function produces a hyperedge on the other side. So the reason why this is in blue, so this particular unification that's suggested up here produces another hyperedge. So this is the one that goes across here. So it's on top of the 4 that we've seen that correspond to the data we collect from the experiment, the fullest Randall product introduces new edges into the hypergraph structure. And it's exactly these edges that impose the necessary constraints in order to adhere to the no signaling condition. So we have one edge here, we have another standing edge here. So to go through the whole lot, so we not only have standing edges going this way, we also have ones going this way. This is a mathematical consequence of the fullest Randall product. And in the end, when you compute the fullest Randall product, you get this hypergraph structure, and it has 12 edges. The 4 are the ones that correspond directly to the experiments that you're conducting or simulating. And these are these rectangles, right? And there's 4 of them, so they are the 4 pairwise distributions. but then you have 12 spanning edges between those 4 rectangles, and these are the ones that impose the appropriate constraints on the underlying hypergraph structure and the social probabilities that allow the no signal condition to be adhered to. So now we've got that in place. So I hope you're able to understand at least some of the elements of this hypergraph structure. So the whole idea is that what we do is we program this hypergraph structure into a probabilistic program to allow us to generate these samples. Okay, so this is the program, the whole program, but I'll just take you through some of the elements. So some of you get some value from this. This shows how we can program some theory that's come out of quantum information science into conventional probabilistic programming language and hopefully do some interesting things with them. So here we have, so this is a standard data structure for 0, 0, 0, 1. So this is how you implement the basic underlying structure of the hypergraph here. You see the 12 edges. So there's 12 of these. So for example, this particular 0, 0, 0, 0 really represents this particular outcome. So A equals 0, B equals 0, given X equals 0, Y equals 0, otherwise that's P1. So in this way we can get into the underlying data structure of the program, the basic structure of the 12 edges of the hypergraph. Now this is the interesting thing. So how do you do the sampling? Right, so we've got this underlying hypergraph structure, so how do we generate the samples, which will, in some cases, allow quantum correlations, in others they may not. Okay? So the way we do this is we essentially say, well, we've got 4 Bernoulli processes, and there is a Bernoulli process for each of these the relevant variables. There's one here, there's a Bernoulli process here, and for Y and for X. So essentially what you do is you're flipping these coins, these 4 coins, and based on that, you're identifying a particular outcome, one of the 16 probabilities that's in the hypergraph, and then you're running the sampler thousands and thousands at a time. That's simulating getting experimental outcomes in your experiment. So every time you get an outcome, there will be an update of one of those 16 probabilities, and then you build up your sample that way. The problem that you have, though, is this particular outcome here. So imagine you sample this one, A equals 0, B equals 0, that joint probability given X equals 0, Y equals 0. So that's one of the 16 possible outcomes. The problem that you have is that this particular outcome is a member of 3 different hyperedges. So this is one of the things, the challenges we have is that these hyperedges are necessary in order to constrain the probabilities, but that means that the normalization becomes a little tricky because in your program you have to update 3 hyperedges, right? So that means you're counting the same outcome 3 times, so that you have to normalize in order to get that. This is the normalization condition. We're just essentially dividing by counts in order to get the probabilities back. I'm running out of time, but I think the question is how does this all work? Right. So the example would be the one example we're showing here is a simulation of a superluminal quantum correlation. So this is the maximum violation of the CHSH inequalities. So that is the maximum possible violation is 4. And so we input these correlations and we run this sampler, right, based on this hypergraph structure which constrains the correlations between 2 sides A and B. And then what you get down here is not perfect, but you can see here 3.999, so that we've got a violation of the CHSH computation of the CHSH inequality with a value of almost 4. So this is the maximum possible violation that you can have. So I think to go back to summarise what I've shown in this talk, I haven't talked much about the syntax, but the main element here is these hypergraph semantics. and the potential for forming the theoretical basis of a programming language that manipulates probabilistic models. And the hope we have is that by using this probabilistic program, we can define many sorts of different experiments in order to investigate the contextuality of these phenomena, either by simulations or actually collecting data from experiments and putting them in a probabilistic program and then using the program to determine whether the phenomena is contextual or not. So I think I've said this before, these hypergraphs are flexible. What we're doing is we're looking at a whole lot of probabilistic programming languages to see whether their suitability for this purpose. There are a number of different conditions from programming language theory. You can evaluate languages, so we're looking at these languages carefully. And we'll make a choice then, and then once we've got the choice of the language, we're going to extend it with these hypergraph semantics. And in the end, this is something we'd like to be able to offer to the community. This will be an open source programming language. So those who want to develop probabilistic models, they can use this in order to run their own simulations or analyze the data from their own experiments. So that's our ultimate goal. And the final thing I think is this. The one thing, and this connects the beginning of my talk this connects the end of the talk to the beginning of the talk, because one of the things that I really appreciate about the hypergraph semantics is the way the theory so beautifully expresses that notion of contextuality, where we can't consider our random variables as being global or external to our measurement context. And it does it like this. It says a probabilistic model corresponding to contextuality scenario is this mapping. So the mapping goes from the set of outcomes to 0, 1. Now, why is this definition significant? Because this particular mapping isn't subscripted by any of the edges. So it's exactly this formulation which expresses the assumption that we hold in probabilistic reductionism, that our variables are global to the measurement contexts. Right? So once you define the underlying hypergraph structure, the question is whether you can find this function. If you can't, if that probabilistic function does not exist, that means, as a consequence, that our assumption that our variables are global or independent of the measurement context has failed. And so this is there's a very neat, I think, expression of the intuitions about how contextuality relates to the identity, the functional identity of our random variables, and how these may be intrinsic or tightly connected to the measurement context in which they're used in terms of an underlying mathematical definition. It's the best I've seen, in my opinion. So that's it. I hope that you managed to follow it. There was a lot of things that I covered, and some of it was in a lot of detail, but I hope that you managed to get some of the essential points.
Thank you.